So let's talk a little bit about the final project. You should have just submitted screenshots or maybe a short video clip demonstrating to us that you successfully implemented whatever your first milestone is. This week you're going to be working on trying to write a set of instructions that can be followed by a student next year who's trying to implement your milestone 1. So that's weekly report 4. So I gave you just a few pointers down here. The main thing that we're looking for in weekly report number 4, these instructions, is that you make things not too easy on the student and not too hard on the student, right? So what we're looking for is, can you hit the sweet spot where the student is getting some guidance from your instructions, but you're obviously not giving them the answers. So I tried my best to hit the sweet spot in assignments 1 to 10. There are places where I gave you some code snippets, but maybe I left some parts out. That's really what we're looking for. So for example, too easy would be obviously, here's a code snippet, put this in your code here, take this snippet, put it in this part of your code here, compile and run, and you should see this, right? That's trivial. If you are turning your legged robot into a wheeled robot, for example, it's also not good to just say, turn your robot into a wheeled robot, right? That's too vague. So where sort of in the middle are you going to challenge the students so they learn a little bit more about the bullet physics engine, they sort of have to figure things out for themselves, and so on. Preston is not here yet, so I will pick on him. He's evolving a robot swarm. His milestone number 1 here is to successfully create a wheeled robot, and he has embedded a screenshot here demonstrating that he's turned the legged robot into a wheeled robot. So when we grade Preston Libby's weekly report number 4 next week, we're going to be looking to see that there's step 1A, 1B, 1C, 1D, and so on that allows the student to incrementally turn the legged robot into a wheeled robot, right? That you've now taken your first milestone, broken that in turn down to a bunch of bite-sized chunks, and described them in easy-to-follow instructions for the student. Make sense? Any questions about that? Pretty straightforward. Now again, for some of your milestones 1 and 2 may be much larger than other people's milestones 1 and 2, so we'll leave that up to your discretion. If your first milestone is sort of a trivial change, we would expect to see a little bit more, maybe expanding milestone 1 when you're including the screenshot and the instructions there. Yes?
If we notice after the fact that we're like essentially our velocity through completing the milestones is a little bit faster, can we add more, or is it now fixed at what we have added?
Okay, that's a great question. You are free to change your milestones however you want, right? So we asked you to try and break things down 2 weeks ago, but obviously now starting to plow your way through your milestones, some of you may be going slower because each individual milestone has a lot of functionality in it, or you may be going faster because you have a lot of milestones that have relatively little functionality in them. That's fine either way. You're free to change them however you want, right? The main thing that we're looking for in the final project, when we start grading them after the final exam period, what we're looking for is by the end of your last milestone, you've implemented something relatively ambitious, but you've done it by breaking things down into a large number of milestones where each one builds on the one after it. If your set of milestones at the end doesn't look anything like your original set of milestones, that's perfectly fine. Preston, I was picking on your assignment here just to sort of show what we're doing. So for those of you that just joined us, we were just talking about weekly report number 4, where you're going to try and write a set of instructions for next year's students for them to successfully implement your first milestone. And what we're looking for in weekly report 4 is that you're hitting a sweet spot in terms of pedagogy. So you're not giving the students the answer, you're not giving them all of the code that they should just plug into their system to, for example, turn their legged robot into a wheeled robot, and you're also not being overly vague. You don't have one instruction under milestone 1 that says, turn your legged robot into a wheeled robot, right? We want to see that you've written your instructions in a way that challenges the students but also guides them, right? So you might introduce some new functionality in Bullet, but then allow them to try and figure out how to use those new commands in Bullet to change your wheeled robot into or change your legged robot into a wheeled robot. Yeah. Okay, any questions about the final project? You just heard me mention, if you have to change your milestones as you go, that's perfectly fine, right? We wanted you to sketch them out front to try and think ahead to how to break your project into bite-sized chunks. As you go, if you find it's useful to restructure your milestones, that's perfectly fine. Okay, so let's get back to lecture. I forgot to mention, I forgot to bring the attendance sheet for today, so everyone is by default present today. Okay, so we're working our way through this 2-lecture segment on collective robotics. So we have a large-scale task that is probably going to be beyond any one complex robot. So we're going to approach this problem as a roboticist, not with a single complex robot, but trying to design a bunch of relatively simple robots that coordinate their action and together are able to carry out a task that would be beyond the ability of any one of them. Right? So coordinate the task. What do we actually mean by coordination? That's what we're looking at in lecture 22. How would a bunch of robots coordinate their action to achieve some collective goal? And of course, since this is a class on evolutionary robotics, can we evolve those coordination strategies? As your coordination, as a group of cooperating individuals becomes larger and larger, and the kind of coordination that group needs to carry out becomes more and more complex, there is a very useful tool that will allow you to coordinate in a more complex way, and that's to communicate, right? So we're going to look at coordination today. We're going to look at some evolved robots that do not speak, they do not communicate. And then in lecture 23, which we'll probably finish today actually, we'll look at robots that actually evolve language or the ability to communicate. Okay. So back to lecture 22. Obviously there are a lot of examples in nature of animals that coordinate action in relatively large groups, and there are very good evolutionary reasons for them to do so. Last time I walked you through the Boyd's algorithm. This comes from the 1980s and comes from computer graphics, where we have a whole bunch of these very simple agents called Boyds. There is no one Boyd in charge. They all are running exactly the same program, and that program is made up of these 3 functions. Each Boyd computes these 3 functions and then sums the and each individual Boyd then sums the results from these 3 functions, and these 3 functions output a desired change in heading for that Boyd, right? So each Boyd at every time step is separating a little bit from its neighbors, aligning its heading a little bit towards the average heading of its neighbors, and cohesing or moving towards the perceived center of mass of its neighbors. If you have a whole bunch of Boyds, they're all running the same algorithm, you get beautiful flocking and all sorts of things, and this has become a standard tool in a computer graphics person's toolbox. It's a standard toolkit in Hollywood these days. You can create more functions, you can weight them differently, and you can fine-tune the behavior of the swarm as a whole. The Boyd's algorithm is obviously something that's written by hand. What if you want the group to do something a little more sophisticated than just moving in the same direction? Well, we started to talk about that last time by thinking about how to actually evolve coordination strategies. And the researchers whose work we're looking at today took inspiration from predators and prey, where it is definitely in the predator's interest to coordinate, because one predator chasing one prey is going to have a pretty hard time, right? It's not impossible for a single lion to catch a gazelle, but it's pretty difficult. It's easier for a pack of lions to bring down a gazelle because they can coordinate, right? Okay. So the questions we're tackling today: can we evolve behaviors for a team of predators in this case? How would we go about evolving it? And will they evolve to cooperate if we run this evolutionary algorithm? We looked at the simulation environment last time. This was a paper that was published before physics engines existed, so this was a very simple simulation. They have an infinite two-dimensional plane. The four edges of the plane in the picture here wrap around and connect to each other. We have one gazelle G and four lions L1 through L4. In this experiment, the behavior of the gazelle is going to be fixed. The gazelle at every time step is always going to move away from the lions, and we are going to evolve the behavior for the lions. Okay. At each time step, the lions can sense the gazelle, and the gazelle can sense the lions. Okay, we ended with slide number 9 last time, where we looked at the hand-coded behavior for the gazelle, and we saw that the next movement and that the behavior of the gazelle is a vector. So it indicates which direction the gazelle is going to head in and the magnitude of that vector. And that vector is determined by summing up each of the 4 vectors that connects the gazelle to the lion. We saw that this sum is weighted by the length of this vector, and by dividing by the length of the vector, we ensure that the gazelle is reacting more to lions that are closer to it, and reacting less to lions that are further away from it. We do this sum, this multiplicand here normalizes it, and then the minus sign ensures what? Moves away from the lions, not towards it, right? So the behavior of the gazelle is programmed at every time step. This is what the gazelle does. Figure out where the lions are and move away from them. Okay. So that's the gazelle. Now let's talk about the lion's behavior. And in this research project, the behavior of the lions was evolved using a particular evolutionary algorithm called genetic programming. And we mentioned genetic programming back at the beginning of the course. What distinguishes genetic programming from some of the other evolutionary algorithms that we've seen in this class?
The genotype of tree, and they just represent a different area.
Exactly. So the one thing that distinguishes genetic programming from all other evolutionary algorithms is the data structure of the genotype, which is a tree, right? So in assignment 1, you had a hill climber and the genotype was just a matrix or a vector of numbers, right? The nice thing about encoding a genotype as a tree is that we can add or remove parts to the tree. We can grow or shrink the genotype relatively easily. Okay, so what's listed on this slide here are all the terminals and non-terminal nodes that can make up the tree that encodes the behavior of the lion. So in order to build up an intuition for what genetic programming is doing here, we're going to actually create some random trees and try and mentally simulate how well a lion using that genotype would do at catching the gazelle. So you'll notice the first 3 here, the number of arguments is 0. That indicates that those are terminal nodes. So we have 3 possible terminal nodes, one of them called last, which is going to return a unit vector that points in the direction that the lion went at the last time step. And at the first time step of the simulation, the last just returns a random, I think that should say a random unit vector, not a normal vector. Same thing with rand-dir here, that also returns a random unit vector. And gazelle will always return a vector that connects the lion to the gazelle, right? And it's the vector that is the smallest vector that connects the lion to the gazelle. Remember that this plane wraps around, so there's different ways in which the lion might sense the gazelle. It always senses it closest. Okay, so let's make a genotype. I'll just use L for last. This is a tree that's made up of a single node, and this is called last. Let's take our gazelle, drop it onto the virtual Serengeti. Let's take the lion, drop it at another position on the virtual Serengeti, and now we start running the simulation. So the gazelle is going to move away from the lion. What is the lion going to do at the first time step? Let's draw our virtual Serengeti over here. Let's say we drop the lion at this point on the plane. What is the lion going to do?
Go in a random direction.
Move in a random direction, right? Last returns a vector that points in a random direction. It goes this way. Let's say the gazelle is up here. The gazelle senses the lion, and the gazelle moves in this direction. All right, that's time step 1. Let's move on to time step 2. What does the lion do at the next time step? It executes this tree, and this tree, which is made up of a single node, returns a vector. What vectors return this time? Same one, right? The last vector in which the lion moved. So now the lion is here. The gazelle maybe moves like this, right? And we keep running this simulation into the future. How does this lion do at catching the gazelle? Not very well at all, right? So if this was our genotype, it would probably get relatively low fitness. It doesn't do a very good job at capturing the gazelle. All right, let's try a different genotype. Again, a single node in the tree, now with a random vector. What does this lion do? Moves around randomly, right? How is that lion going to do at capturing the gazelle? Not very well at all. Let's try a third one, G for gazelle. All right. Let's put the lion back here, and let's put the gazelle back here. So the lion moves 1 unit vector towards the gazelle. The gazelle is 3 times faster than the lion, moves away. The lion moves towards the gazelle again, and the gazelle is gone, right? So none of those 3 trees are doing a very good job at capturing the gazelle. Now again, we're not being very fair to the lions because we're only allowing 1 lion for a moment. We haven't moved on to collective action yet. We're just trying to build up an intuition for what our evolutionary algorithm is doing. So let's imagine that we had created a population of random trees, and the first 3 trees in that population were the 3 trees that we just mentally simulated. Those would all get relatively low error. Let's try a slightly more complicated tree. We can see that there are non-terminal nodes here that perform computations on vectors. So what the trees are doing in this case, every node in the tree always returns a vector. So let's create a non-terminal node with plus, and let's create 2 subtrees at random for this tree. Let's create random direction plus gazelle. Okay, so at every time step, this returns a vector that points towards the gazelle. This returns a random unit vector, and those 2 vectors are summed, and the root of the tree returns a vector, which dictates the movement of the lion at the next time step. How does this lion do at capturing the gazelle? What does the behavior actually look like? It moves towards the gazelle.
And that has another vector that moves it in a random direction once it gets there.
So we're actually, at each time step, we're evaluating the tree, right? So we take the vector that connects the lion to the gazelle, we create a random unit vector, and we sum those 2 vectors at just 1 time step, and we return that summed vector, and that's what the lion does at the next time step. At time step 2, we again compute the vector that connects the lion to the gazelle, add on a random vector, and that's the behavior of the lion at time step 2, and so on. How does the lion move across the plane?
It moves like in the direction of the gazelle, but off the side, depending on the random vector.
Exactly, right? So generally it moves towards the gazelle, but it's doing it with a little bit of randomness in its direction, right? But generally it's moving towards the gazelle. Turns out if you simulate this lion does slightly better by a small amount compared to the lion that just goes straight for the gazelle, right? It's kind of fainting a little bit as it approaches. So not great, but slightly better, right? So again, we're imagining a population of these trees that are evolving, and we're assigning fitness to each individual tree, which is how close does the lion manage to get to the gazelle, right? Okay, we could multiply the magnitude of a vector by 2. So let's imagine a slightly more complex tree. Is it multiply by 2? Multiply by 2, and this one just takes one argument. What is this lion? What does the lion do that executes this genotype? How does it move?
It's the same way as before, but now more exaggerated.
It's just a little bit more exaggerated in how it moves, right? So you can see as we create trees that are made up of these vectors and vector operations, we can alter how the lion behaves relative to the gazelle. You can see that there's some complicated non-terminals down here. Let's try and think through what these actually look like. Let's take the if dot non-terminal node. This non-terminal node takes 4 arguments, so we need 4 subtrees. And I won't fill these in. These could be anything. They could be terminal nodes, or they could be trees in and of themselves. But we know that each of these 4 subtrees returns a vector. So the if dot non-terminal node takes the vector returned by the first tree and takes the dot product between that vector and the vector returned by the second subtree and looks at the dot product of those 2 vectors. And if the dot product is greater than 0, return the vector of the returned by the third subtree. If the dot product is less than 0, return the vector returned by the fourth subtree. So this terminal node is always returning a vector, which is either this vector or this vector. Right? We've introduced conditionals now using vector operations. And same thing goes for if greater than or equals to. Right? So what evolution is doing, and what we're going to look at in a moment, is obviously evolution evolving behaviors for lions. What evolution is really doing is evolving increasingly complex vector operations, which ends up controlling the lion on the plane. And the fitness of any one tree is how close the lion gets to the gazelle. Sound good? Okay, Tyler.
Is the final output vector of that tree normalized to be 1 unit?
The final vector is always normalized to be 1. That's right. So whatever it's returned, it's always 1 because the lions can only move 1 unit per turn. That's right. The gazelles always move 3. Right? So it'd be easy for evolution to cheat. Just make a vector that points towards the gazelle and increase the magnitude of that vector. Right? It's always normalized to 1. Okay. So we just walked through making 4 or 5 trees. If we took 4 lions now and we dropped it on the plane, and all 4 lions were running the exact same tree, what should those lions do? Can you construct a coordination strategy for those 4 lions using the vectors and the vector operations you see here? What happens if all 4 lions were just running G? So all 4 lions dash towards the gazelle. It just runs away, right? Still not very good. So G doesn't work well for 1 lion. It also doesn't work so well for 4 lions. What if all 4 lions were running the tree where the lion approached the gazelle but moved a little randomly? How would that lion pack do? Slightly better, but again, still the gazelle could probably outwit that lion pack. Yes?
If you use the if dot, the dot product is giving you sort of a bearing of angle on it.
Could.
So you could have lions on the left go, it would coordinate left and right around.
Exactly, right? So you could have lions on the left moving to the left, and the lions on the right going to the right. But how does a lion know whether it's on the left or the right of the gazelle? Doesn't know, right? There isn't enough here for the lions to know. So what the investigators did in this project was to take this base set of non-terminal and terminal nodes, evolve lions using this set. Then they added some additional operations, re-evolved the lions, and measured whether the lions did better. So the first expansion pack, if you like, that they gave to the lions was a set of operations that allow the lions to perform deictic sensing. And deictic sensing is exactly what Preston was just mentioning, which is sensing things in a relative manner, right? So Preston is on my right, is on my left, Barry is on my right. I am sensing things relative to my own position in space. That's deictic sensing. When you tell someone, can you hand me the glass that's on your left? You're giving them a deictic command, right? If you tell that person, give me the red cup, that's absolute sensing, right? It's not relative to the observer. Okay, so how can the lions deictically sense? Well, we're now throwing in 4 additional terminal nodes. The first one, nearest, returns a vector that connects the lion that's nearest to the gazelle to the gazelle. So imagine there's 4 lions out on the plain. They're trying to bring down the gazelle, and one lion executes the tree that has nearest. If that lion happens to be nearest the gazelle, then it's the vector that connects that lion to the gazelle. If that lion is not the closest lion to the gazelle, then nearest returns a vector from one of its buddies to the gazelle. Right? As the lions move around from one time step to the next, that vector might suddenly shift because one lion is now closer to the gazelle than another one. Make sense? Remember, all of these operations, or all of these terminal nodes and non-terminal nodes are always returning a vector. Okay. Lion returns a vector that connects the lion that's executing the tree to its closest ally, right? Whatever lion is closest to it, that's the vector. Our lion returns a vector that connects me to the closest lion on my right. So I start by putting out a distance sensor, if you like, directly in front of me, and that starts to sweep clockwise. And the first lion that sweep comes into contact with, that's the vector that's returned. I know where the lion is on my right. L lion, same thing, cast a distance sensor directly out in the direction that I was heading, start to sweep that vector counterclockwise, and whenever it hits the first lion, that's my L lion. That's the vector that connects me to the lion that's on my left. Okay, if we add this set to this set, we could probably construct a tree that implements Preston's idea, right? Lions that are to the left of the gazelle move a little bit to the left and around, and lions that are on the right of the gazelle move a little bit to the right and around, and then maybe they start to approach. That's one possible strategy. There may be others. Okay, so that's deictic sensing. Again, let's go back to the base set, and instead of adding deictic sensing, let's add name-based sensing now. So now we're adding 4 terminal nodes, and each of those 4 terminal nodes returns the vector that connects lion 1 to the gazelle, or lion 2 to the gazelle, or lion 3 to the gazelle, or lion 4 to the gazelle, right? So now this is like reach for the red cup. Now, if I'm a lion that's executing, I'm trying to bring down the gazelle with my colleagues, and I execute lion 1. If I'm lion 1, then the vector that's returned is the vector that connects me to the gazelle. If I'm lion 3, then I get back a vector that connects lion 1, who may be on my right, but I don't know that. I just know it's the vector that connects lion 1 with the gazelle. So we're going to look at 3 sets of experiments in a moment. One set of evolutionary runs where they evolved lions to bring down the gazelle using this set. A second experiment that contained this base set plus deictic sensing. And then a third experiment that contained the base set plus name-based sensing. Before we go any further, anyone want to take any bets? Which pride of lions did better? Those with a base set, those that were sensing diacritically, or those that were sensing based on names? Why names?
It's the best kind of communication. You're not limited by, with diacritic, you have to be close to the other lions, versus names, they can be anywhere.
They could be anywhere. What does that allow? So it is a little bit more flexible if you have name-based sensing, but what additional aspect of coordination does name-based sensing allow that the other two do not allow? So when you work in a large group or you go play a team sport, right? Take positions, right? And what do you do when you take a specific position when you're playing a sport?
You have one specific role.
You have one specific role, right? Specialization, right? Not everyone is doing exactly the same thing like in the boys. So is specialization useful in this admittedly simple task, right? Well, let's see. Okay, before we actually look at the evolutionary runs, there's one other additional methodological wrinkle that we need to consider, which is, remember that we're evolving a single tree here, but that tree is going to be used by 4 lions, right? So how do we actually do this? We have one genotype, but in a sense we have 4 phenotypes, which are the 4 lions. Remember our discussions about genotype to phenotype mapping. How do we actually use our tree to control 4 lions? We need to think about how to map this genotype onto 4 phenotypes. The simplest thing to do is, again, taking inspiration from the Boyds, we can use cloning. So we have our population of trees. We take each tree out of the population. We make 3 copies of that tree. So now we have 4 copies of the tree, and we drop those 4 identical trees into the 4 lions. They're all executing exactly the same plan like the Boyds do. Do the lions all do exactly the same thing? We have the 4 identical copies of the genotype. And we have 4 phenotypes, which is the trajectories of the 4 lions. Do we get exactly the same 4 trajectories? Why not? Different initial conditions, right? The lions are at different positions on the plane. They have different relative positions to each other and to the gazelle, right? So we can have identical genotypes but get slightly different phenotypes. That's fine. So we can do cloning. We can do free breeding, which is we're now going to add an additional constraint to each of the trees in the population, which is that each tree has to have a root, and under that root there have to be 4 subtrees. The root itself, this node, is empty. And we just have these 4 subtrees, and each of the 4 subtrees dictates the behavior for each of the 4 lions. So we still have one tree, and that one tree is dictating the phenotypes of the 4 lions. But now our 4 lions can have different underlying programs. They might be executing different vector operations, and obviously also doing different things. Okay, so imagine that in our population we have a bunch of these trees, and we want to create a new tree, right? We've evaluated all the trees in generation 1. We want to cross and mutate those trees to produce new lion strategies. We can do free breeding, where we start by creating a new tree that has an empty root, and we pick an individual. We take this subtree, we introduce some slight mutations, or we take the subtree, copy it, mutate it, and plug it in as subtree 2. We pick at random the first subtree from this tree, make a copy of it, mutate it, and plug it on as the 4th subtree, and do that 2 more times, and we now have we have a tree that is made up of 4 subtrees. Right? So we've created a new tree in the population, do it again and again and again to replace whatever trees were killed off in the first generation. Okay, so that's free breeding. Third one we're going to consider is restricted breeding. We're going to do the same thing we did in free breeding, but now when we're constructing a new tree and we're constructing the kth subtree in the new tree, we can only copy and mutate a kth subtree from one of the existing trees in the population. So if we're creating a new strategy for lion 1, we can only use strategies from other lion 1s, right? And when we're creating the subtree for L2 here, we have to pick L2, only L2 from some other tree in the population, copy it, and mutate it. Right? So every kth subtree in every tree, its ancestor is some other kth subtree from some tree in the previous generation. We're still mixing and matching strategies for different lions from different trees, but it's always inheriting from the same lion in the pack, in the pride. Okay, so we have 3 different ways of evolving trees. And we have 3 different kinds of trees, right? Trees with this set plus this set, and trees with this set plus this set. So that gives us a total of 9. That gives us a total of 9 experiments we're going to perform. We're going to perform an experiment with each of the 3 different ways of sensing, and for each of those 3 ways of sensing, we're going to consider the 3 different team construction methods. Make sense? A lot of combinations and permutations of experiments here. So 9 total experiments. For each of those 9 experimental settings, they did 100 evolutionary runs, and they wanted to see on average, among those 100 evolutionary runs, how well did the pride of lions evolve to bring down the gazelle, or did they bring down the gazelle? So that takes us up to a total of 900 runs. They did an additional set of 100 runs with 1 lion, evolving behavior for just 1 lion, 100 runs with 1 randomly moving lion, and 100 runs with 4 randomly moving lions. It's a little misleading because they're talking about runs here. It's just on average, how well does 1 randomly moving lion do? On average, how do 4 randomly moving lions do? And how well can we get 1 lion to do at bringing down the gazelle? Yeah. So that gives us 900 runs plus an additional 300 runs, so a total of 1,200 evolutionary runs in this case. And in the next few slides, we're going to analyze the results from all these experiments. For each one of these evolutionary runs, they did 51 generations. So the first generation are just random trees, and then they evolved those random trees for 50 more generations. At any one time, they had 500 trees in the population. Trees could evolve to be bigger or smaller, but they could never evolve to be bigger than 70 nodes, and they could never be deeper than a depth of 17. These kind of seem like arbitrary numbers, but these come from the early literature on genetic programming. Okay, so for each tree then, right, we've got a very large number of trees now that are going to be evaluated. We take that tree, we place the gazelle somewhere randomly on the plane. We take the 4 lions, we place them at random positions on the plane, and then everybody gets to move for 15 time steps. Fitness is equal to 0 if there is at least 1 lion that is less than or equal to 1 unit from the gazelle. That's considered a kill. That's the best you can do, right? So the lower the value here, the better. And if the lions don't get within 1 unit of the gazelle, then whatever. That's the fitness value, right? The higher the number, the further the closest lion was from the gazelle. So far, so good? Okay, let's look at some results. We're going to make a number. Here's our results up here. We're going to parse the results here by making a number of observations as we go. So let's start with the 3 control cases. Right? we can see that one evolved lion on average ended 7.3 units away from the gazelle at the end of those 15 time steps. If you go back and do the math, that's about as bad as you can do, right? The gazelle is as far from the lion as you can possibly be, right? So one lion, even evolving behavior for it, doesn't do very well. Sorry, I misspoke. Actually, you can do slightly worse, which is what the one random lion did, not surprisingly. So one evolved lion doesn't do much better than one random lion. And by going through these example trees, you can probably see why, right? There's not much that one lion can do if it moves 3 times as slow as the gazelle. Four random lions do better than one lion. Let's just focus on the random case for a moment. So the 4 randomly moving lions, one of them was on average 4.4 units away from the gazelle at the end of the 15 time steps. Why? Why do 4 random lions do better than one random lion?
Because based on the placement, even if the lion is going like this way, one of them's going this way, one of them's going this way.
Right.
The gazelle still has to avoid those other ones.
That's it. Remember that this is a toroidal plane, right? It's a donut. So although it's infinite, although the gazelles and lions can move an infinite distance, the plane itself is finite. So by definition, if it's a toroidal plane and you have 4 lions, most of the time the 4 lions are surrounding the gazelle just by chance, right? So really when we're talking about 4 lions, this is the baseline that we should be thinking about, right? Can we do significantly better than 4.4 units? And if we now start to look at our 9 experiments up here, and we look at the averages, we can see that all 9 averages are significantly below random. That immediately tells us that if we have 4 lions, and no matter how we evolve them, they can do better than random. So even in this simple task, there tends to be things that 4 lions can do to coordinate their strategy to get closer to the gazelle than moving randomly. Okay, let's break this down a little bit more. For clones, so remember that clones here means that each of the 4 lions is executing exactly the same tree. When we were producing trees using this cloning method, name-based sensing was worse than deictic sensing. That seems to contradict what Barry was saying, which is that name-based sensing probably is better than deictic sensing. Why was name-based sensing worse than deictic sensing when we were cloning the behaviors of the 4 lions? There's cloning at the top there. Yes?
We mentioned that the name-based system, that the advantage was in positions, having specialized roles, and maybe they don't.
Exactly. Right? By definition, if you're cloning the behavior, there are no specialists. And name-based sensing gives you an advantage, which is if you have name-based sensing, you should be able to exploit specialization if you can specialize. But with cloning, you can't. Right? Okay. For restricted breeding, so now let's have a look here. We can see in restricted breeding that name-based sensing does better than deictic sensing. Right? So now Barry's intuition is holding up. Right? When we have restricted breeding, let's go back to that for a moment. Restricted breeding down here, evolution is continuing to improve the behavior of L1 and continuing to improve the behavior of L2, L3, and L4. So if, for example, L1 starts to specialize and always runs out ahead of the gazelle, it's offense, if you like, right? It will continue to be offense depending on what the mutations do, but it can keep that specialized role in the new tree, and if L2, L3, and L4 are flushers, they're coming around the side, they can continue to do that, right? So for example, L2 in the new tree can be relatively confident, with quotation marks, right, that L1 is doing what L1 is supposed to be doing, so forget about L1 and focus on what you're supposed to be doing. You're not trying to guess what it is that L1 is doing, right? L1 has evolved a specialized role, and you do what you're supposed to do based on the assumption that L1 is doing what it's supposed to be doing. Right? So the hypothesis here is that name-based sensing here with restricted breeding is the beginning of specialization, and if you look at all 9 of these averages here, that was the best strategy. So whatever it is that the lions are doing here, there is probably specialization emerging in that one set of 9 experiments. The heartbreaking aspect of this paper, they never actually showed you what any of these evolved strategies are. So if you're very curious, and I know some of you are evolving predator and prey robots, make sure to show us how your swarm coordinates behavior, because you won't find it in this paper, unfortunately. Okay, but there is indirect evidence here that this team is starting to specialize. Okay, so that's as far as the investigators took this experiment. We start to get specialization here, and as I just said in this example, if I'm L2, I'm just going to assume that L1 is doing what L1 is supposed to be doing, which may be easy to do in this relatively simple task. But what happens if we continue to evolve these robots to do more and more sophisticated and complex action? It may become increasingly difficult for me as Lion 2 to always know what L1 is doing. I have to try and guess all the time what L1 is doing in order to do what I'm doing, right? Now I may look at L1 and try and infer from how L1 is moving what it's supposed to be doing, but there's a problem with that. If L2 has to rely on observing L1 to try and infer what L1 is doing, what's the limitation of that strategy in terms of coordination?
There's a time delay.
Perhaps there's a time delay, that's right. What else? What's that? You have to be able to see L1, exactly, right? What if we're hunting in a forest or otherwise obstructed environment? That's going to be a problem. What else is a problem?
I think if they have different genotype trees, they wouldn't be able to understand each other's motions so well either way.
That's right. At least in this experiment, there's nothing in here that's going to allow the tree to interpret what the other lion is doing. We've been talking about the lions, we've forgotten about the other player here. Any baseball fans here? Why does the third base coach not act out what he or she wants the batter to do? Why all the, right? Because the gazelle will see, right? So there's lots of reasons why coordination in a lot of species eventually led to the evolution of communication. One of them is deception, right? But another one is it lessens my cognitive burden. If I'm trying to always guess what L1 is doing, and maybe doing it by actually watching L1's movements, it would be a lot easier to me if L1 could just say, I'm going left, you go right, right? Okay, so now we're going to move to a different experiment, which sort of, in a way, picks up where the previous lecture left off. One of the students last year nicknamed this pair of lectures the sex and violence part of the course, right? We just did violence, now we're going to turn to sex. Now we don't have lions and gazelles, now we have female and male robots. This is an even older paper, actually, than the one that we just looked at. So now we don't even have a continuous two-dimensional plane. Now we have a grid, and these male and female robots can occupy individual elements in this grid. And as you can imagine in this experiment, they're again going to use an evolutionary algorithm to evolve communication between these male and female robots. Okay. So we have a 200 by 200 grid. Again, it's toroidal. So if you move left past the left-hand edge of the grid, you end up on the right-hand edge of the grid, and the same thing for top and bottom. They're going to start by seeding this 40,000 element grid with 800 female robots and 800 male robots. The females are deaf and immobile but can signal, and the males are blind, they can hear, they cannot signal, and they are mobile. Okay, so lots of relative advantages and disadvantages for the two sexes here. Why did they actually do this? You can see this in the cartoon here. The females are actually going to be able to signal. They're going to emit a call that can be heard by any males that happen to be within the zone of the female. The male at any time step can move 1 unit forward, it can stay still, or it can turn 90 degrees to its left or 90 degrees to its right at every time step. Each of these 1,600 agents is equipped with a neural network, not unfamiliar, not that different from what you've seen before. This is the neural network for the females. These are the neural networks for the males. You can see that in both cases we have an input layer, a hidden layer, and an output layer. We can see that there are recurrent connections at the hidden layer, which means the males and the females can remember, if that's useful here. The input and output layers, however, are different for the males and the females. Let's start with the females. I'm sorry, and I also forgot to mention the input and output. The input and output for most of these layers are binary. So the input for the female neural networks is the position and orientation of the closest male in her visual range. So going back to this cartoon for a moment, I'll come back to this slide. Let's take this female here. A male is now southeast of her. So again, this is deictic sensing from the point of view of the female. The female now detects a male that is southeast of her, and that male is pointing south. Right? We have two pieces of information, which we can then feed in as a binary vector up here. So each individual input neuron represents a male to the northwest, or a male to the north, or the northeast, or what have you, right? And then this represents, is the male that I'm detecting facing north, west, south, or east? You can construct that as a binary vector. So in this little cartoon here, this particular female is detecting a male that is southeast of her, and that male is facing east. So far, so good? Okay. Then we update our neural network as usual, and they apply a specific activation function to the output neurons here, which round these values to binary values. And these binary values are the song produced by the female. That's it. That song is heard by the male, right? So that male that is southeast of the female receives as input that binary vector, right? So this male hears this female. We update the neural network of the male, and now male network. We update the male network here, and we then look at the output neurons. A different activation function is applied at the output layer, which scales the output values to integers. And there are 4 output neurons. One that is associated with staying still, one that's associated with moving forward, a third one that's associated with turning left, and a fourth one that's associated with turning right. So we have 4 integers arriving at the output layer of the male network. We look to see what is the largest positive integer among the 4, and that's the action that that male performs. Okay. So we've got these 2 types of neural networks, 800 of these for the females that are scattered across the grid, these 800 that are in the males that are also scattered randomly across the grid. What happens as evolution starts to change the weights of these synapses? What is changing about the behavior of the males or females? We haven't said anything about what the fitness function is here. Probably guess what it is. But what happens in general? What happens as, let's view things for a moment from the point of view of the female. What happens is the male starts to move through her territory.
She's going to start calling.
She's going to start calling, right? So as the input layer changes, because the male is moving through her environment, she may or may not change the song that she is singing, right? If we change the synaptic weights for that one female and the same male moves through her environment in exactly the same thing, what happens?
It's going to be a different call.
It's going to be a different call, right, or a different song.
That's sort of like the male has to evolve to interpret the calls of the females.
And so the males are going to have to evolve
And
to...
the females obviously going to have to evolve to be able to call them in a way that they'll get.
The evolution of communication is always tricky because two things need to happen together. The speaker needs to speak appropriately, and the listener needs to interpret appropriately. If either of those conditions is not met, whatever song is being emitted is useless.
I feel like it would make sense to start with a very small grid so that because it's going to start out random, but
It's going to be absolutely random.
if it's a very, very small grid, then the one time when the call is interpreted as go to the left, and then it does work out. I assume, the fitness function is them.
Getting together,
Getting
right?
together, yeah.
Yes.
So the time when that happens will be rewarded, whereas I don't know, if we start with a grid of 3 units out, it's going to take a really long time.
It could. Turns out it actually doesn't take that long, and we'll see why in a moment, right? But keep that in mind, right? It seems on the surface to be a pretty difficult thing. Females need to emit the right song at the right time, and males need to react to the right song at the right time for the two of them to get together, right? So back to the male network for a moment. The male hears a song and reacts somehow according to what it hears. If evolution alters these synaptic weights, it may or may not change how the male responds to a given song. Okay, so absolutely, the fitness function here is sex, to get together. So remember that the males can move, but the females cannot move. So as this simulation runs forward and the males are moving around initially at random, if one male ever occupies the same cell as a female, the male and the female each produce a new male and female network, which is a mutation of the network. There's actually no crossover between these networks, so it's sex without sex, if you like. Right? So the males and females produce, so the male produces a new male, which overwrites some other male somewhere in the population, right? So there was a male sitting here. This male is killed off, and the mutated version of the male parent is placed here. Right? Same thing with the female. The female produces a mutated copy of its neural network, and that new female network overwrites some other female network randomly somewhere on the grid. You take the male and female parents, you separate them, and you put them at new empty positions at random on the grid.
This probably wouldn't matter too much, but can they overwrite themselves?
I think they could. I don't think they did that in this case. Right?
Yeah, I can see it having too much of an effect.
You want the parents to keep producing more copies of themselves, right?
Right.
Now this is actually, if you think about it, a very different evolutionary algorithm from any we've seen before, right? All of the evolutionary algorithms we've seen before, we have a population of genotypes, we evaluate the fitness of each of them against a fitness function. The ones that get low fitness values we delete, and those that have high fitness values, we make randomly modified copies of them to produce our new population, do it again and again and again and again.
So that, again, the children are random, they're not crossed over.
They're mutated copies of the parents, but we're not combining the genetic material between the male and the female network. We have one male and one female network here, so 2 networks. We take those 2 networks, we produce copies of them, and we introduce mutations when we copy them, which gives us 2 new males and females. The new male overwrites some other male somewhere in the grid, and the new female network overwrites some other female network somewhere else in the grid. The original male and female parents, we just put them at new positions in the grid. We separate them. Otherwise, they'll just produce two new children at the next time step. Right? That's cheating. Okay, so where's the fitness function here? Where's the equation that the computer uses to measure the fitness of males and females? There isn't one, right? Like nature, there's no fitness function in nature. It's how many offspring can you produce, and how long can those offspring survive, and how many offspring can those offspring produce, right? So although this paper is quite old, this is a much more biologically plausible evolutionary simulation than what we've seen before. There's also no generations here, right? It's just at every time step, we just keep updating this simulation. The males move around, and at any time step, if a male manages to occupy the same cell as a female, they produce two children, and away you go, right? That's it. Pretty simple. Yes?
Is there a way to remove organisms from the simulation if they don't reproduce, like old age or something?
Absolutely. What happened to the male that was sitting here? This male was deleted and replaced with the male child produced by this parent. That's how individuals are deleted. They get overwritten by children produced by parents that manage to mate.
But that male could have been useful.
Could have been.
Had some, but like if it was headed straight for the female and we deleted it right before it got there.
That's life, right?
Nature's
No one said Mother Nature is kind, right? There are many parallels to be drawn between these male and female robots and male and female humans and animals, right? Mate as often and produce as many offspring as you can. You're slower at that, doesn't matter how close you got, there's no second place prize in evolution, right? Either you made it or you didn't. Okay, so our population size always remains constant, right? Because when these two parents produce two new offspring, two other individuals in the population get deleted. So we always have 800 males and 800 females. So far, so good? Okay. Okay, so let's actually have a look at what happens. So I'm going to show you a number of tables now. One of the nice things that is because this simulation is so simple, we can look at basically just tables of results. So after, remember they have this simulation, they put 1,600 of these agents at random, and then they update the simulation. After 100 time steps, this is what you see. They looked at all of the males, and they saw what did the male do when the male entered a female territory, and that female happened to emit the signal 000. Of all the males that ever heard this song produced by any female at this time step, 25% of them moved forward, 38% of them turned right, 9% of them turned left, and 28% of them stood still. Of all the males that heard 001, on average, a quarter of them did one of the four actions. So what's happening here? What can you infer from male behavior at this point? It's just random, right? As you would expect. At this point, for each of the 8 possible songs, the males just did random things. After 5,000 time steps of the simulation, this is what's happening. Most of the time, the males are just moving forward. Why is that better than doing things at random?
Because any kind of change, when you're going to get different sensory input, so if you stay still and you get the same sensory input to make you stay still again and again.
What's your chance of mating if you stay still from the point of view of a male?
No.
What's your chance of mating if you turn left? You're turning in place, right? Turning 90 degrees to the left or turning 90 degrees to the right. If you just do that, what's your chance of mating? 0. If you turn right, what's your chance of mating? 0. If you move forward, what's your chance of mating? Still pretty low, but it's higher than 0. So if you were a male in this simulation, what would you evolve to do? You'd evolve to always move forward. You're wasting time if you ever stop and turn. This is the closest metaphor between male humans and male robots, right? They've evolved the ability to not listen to the females in this simulation, at least so far, right? Just go straight. Again, paralleling male humans, not an ideal strategy, right? There's something that you can do that's better than just moving forward. So what happens? 7,500 time steps later, things are even worse, right? This is not looking very good for the males or the females. They have to wait for a male to randomly come across them, right? Luckily, after 15,000 time steps, this is what started to happen. What are the males doing now?
They're actually starting to, if not orient themselves, then at least sometimes change direction.
That's it, right? So they're taking a risk by stopping and turning, right? And you can see that they're turning left or turning right in response to this song, and left in response to this song, and in response to all the other songs, they're still just going straight. So the fact that there are so many males that are doing that, these males are the offspring of other males and so on. The fact that they exist means there must have been some advantage for them to do so. They must have mated more than the males that just went straight, which means the only explanation is that the females have started to emit a song at the right time and the right place. Here's the explanation up here. In this simulation, by 15,000 time steps, the females had evolved to emit one of these two songs when the male was on the same row or column as the female inside her song radius, right? So when a male is moving and hit the same row or column as a female, she may have been emitting any one of these 6 songs, which from the point of view of the females just means do what you always do, go forward. But the moment you enter the same row or column as me, I'm going to change my song. And for some of the males, actually by now a majority of the males, they turn when they hear that song, which is only emitted by the females when the male is on the same row or column as her, right? So now, at this point, after 15,000 time steps, there has been enough random situations where the females emitted a call at a certain point in time that the males happened by chance to respond to in the right way, which increased the frequency of those males and those females co-occupying the same element, which produced more of them, which means there were more females emitting the right call at the right time, and more males doing the right thing when they hear that call at the right time. So far, so good? Did it have to be song 6 and song 7?
No.
Did it have to be turn left when you hear song 6? It's arbitrary, right? This is just a historical accident of this evolutionary run. Okay. As time went on, after 15,000, the females evolved to emit song 6 or 7 in a larger number of situations. So now, when a male hit any cell within, actually this is now 5 by 5, that's right. Now, whenever a male hit any of these 8 elements, now she would emit the right call. Before, it might have been 4 out of the 8 that she emitted that call, and the other 4, she emitted the other calls, and the males just kept going on their merry way and missed the female, right? So in essence, the females are evolving to widen their net. They're able to attract a larger number of males from different situations.
But if it's in the outer one, and it was told to turn left, right? Couldn't it get into, like, it would have to be fairly complex, is what I'm trying to say.
So let's say the male enters this cell and is facing east. Remember, the female knows that. There's a male to the south that's facing east. She might emit the right call that causes the male to turn 90 degrees to the left.
But then, like, that input, it wouldn't do that call. It would do this forward call whenever.
If it does the same call again,
Yeah.
by definition, the male is going to turn to the left again,
Right.
right? So what does the female do? Over evolutionary time, she evolves to stop making that
Right,
call
right.
at that point, and the male moves forward.
That's cool.
That's what's happening after 15,000, is when the song is emitted is being calibrated by the females that are able to do this. Not all the females are doing this yet. Okay, let's just pause for a moment and have a look at a control setting here. They did a second set of runs now. So the ones that we were just describing is shown by, it's hard to see here, this is a test here. So after 60,000 time steps in the simulation, the males were taking on average 50 time steps to find the females. At the beginning, it was taking on average 250 time steps for any given male to find a female. So the rate of reproduction has gone up considerably over time. The control experiment is exactly the same thing, but now they've deafened the males. So regardless of what song is emitted by the females, the males just do what they want. So not surprisingly, by 60,000 time steps, the males here are taking twice as long to mate with the females as they did when they were not deaf. But what's interesting is if you look here, you see in the initial stages of evolution, the deaf males were actually doing better than the males that could hear. Why?
Could be that the female songs were so random they weren't even helpful.
Maybe. Or the males were not interpreting them correctly, right? The female might have been emitting a song that if the male had turned left, she would have emitted a different song which would have brought the male to her. Perhaps the male listened, heard the song, but turned right instead of left, right? So again, the difference here shows the challenge of communication, right? You need to evolve females that emit the right song at the right time, and you have to have a sufficient number of males that happen by chance to do the right thing when they hear those calls. Once they do, evolution can kind of lock in that pattern, right? You get more females that emit the right call at the right time, and more males that respond appropriately when they hear that call. It's tricky. It's hard to get started. There is this mediocre strategy, which is to just not listen to any call whatsoever and just move straight, right? So in the long term, there is a benefit of communication, but it takes a while for that benefit to kick in because you need both of these things to happen together. Okay. These are just some cartoons showing you what the male and female actually did. So here's the female, she's emitting her call. Here comes the male moving forward, and the male moves forward, and when the male happens to reach the same row as the female, she changes her song. That changed song causes the male to turn, and now she emits the song 101, which this male interprets as move forward. Okay. Here's an example of a better evolved female signal and male response pairing. So now this male is coming in from the top left, moving to the east. When the male happens to hit this row, the female emits this song, which causes most males in the population at this time to turn left. So this male turns left. She knows that the male is to the north and has turned left. So she continues to emit the same song, which continues to cause the male to turn left. And if the male turns left 3 times, the male is now aligned properly, and she changes her song to 0, 1, 1. So with just these 2 songs, If a male comes in from below, she only emits the song once because she only needs the male to turn left once. If a male comes in from the top, she knows that, and she knows to change, she knows that she needs to emit that song 3 times rather than 1. So that female is able to attract males that approach from the north or from the south. Right, an example of a female widening her net. Okay, I think we're out of time, so we're not going to look at this last experiment. We will look at that on Thursday. You have a quiz that is due tonight, and you're now working on weekly report number 4. Thank you very much. And again, there was no attendance sheet for today, so everyone by default is present.
Quick question.
Yes.